Okay, welcome back. Today we start Chapter 2, Modular Arithmetic. And we're going to discuss Section 2.1, Congruence. This is a sort of a new way to do arithmetic and is extraordinarily useful. And we've actually seen it our whole lives a lot. So when we tell time, unless we're in the military, once we get to 12 o'clock, we don't go to 13 o'clock, and instead we go back to 1 o'clock. And instead of saying 14 o'clock, we say 2 o'clock, and so forth. And in general, when you're dealing with time, you can subtract multiples of 12, and that's just called modular arithmetic, mod 12. So here's the official definition. We say that A is congruent to B mod n exactly when A and B differ by a multiple of n, which is another way of saying that n will divide A minus B. So let's go ahead and write that, the alternate way of saying it, that A is congruent to B mod n exactly when A and B differ by a multiple of n. And then we're going to go ahead and write when A is congruent to B with something that looks close to an equal sign, but with 3 horizontal slashes. So A congruent to B. In fact, when you're doing this a lot, often you leave out the mod n part when it's understood, but I'll try to write it most of the time. And in fact, often when people are working with this, if it's understood that modular arithmetic is being referred to, they'll often just write A is equal to B and understand that means congruence. But again, I'll try to write these 3 horizontal slashes so we minimize confusion. All right, here's some examples. So 13 is congruent to 1 mod 12. We've seen that. That's the time. That's because 12 divides their difference. And 14 is congruent to 2 mod 12. And 26 is congruent to 2 mod 12 as well, because their difference is 24, which is a multiple of 12. All right, we only have one lemma in this section, the basic properties. The lemma is completely trivial. It comes just from the definitions. I think we'll only prove one of them, but let me write it down. Okay, so modulo n, we have the following statements. 1, A is congruent to A. It'd be pretty weird if that were not true. Number 2, if A is congruent to B, then B is congruent to A. And number 3, A congruent to B and B congruent to C says A is congruent to C. We have 2 more statements, but shortly we'll see these types of equalities that satisfy these 3 properties get called an equivalence relation, and we'll see that more later. Anyway, number 4 is that modular equality is well behaved with respect to addition, and number 5 with respect to multiplication. So if 2 things are equivalent and you add them, they stay equivalent, and the same is true of multiplication. You start with 2 things equivalent and multiply them, they stay equivalent. All right, let's go ahead and prove, I don't know, just part 4. All right, we just write down the definition and the proof will write itself. So A1 congruent to B1 means that A1 is the same as A2 up to a multiple of n. And similarly for that should be a B2 there, a B1. There we go. A1 and B1 differ by a multiple of n. Similarly for A2 and B2. And then you just add these together. Factor out the n there in that last term, and this is just the definition of A plus 1 being congruent to A1 plus A2 being congruent to B1 plus B2. And that's what we wanted to prove, and that's all we're going to prove. We'll leave the rest for homework. All right, that's it.